Okay, hey everyone. Sorry about the slight delay in kicking off there. I've been MacGyvering some hardware on a table, a chair here, but I think we're set up and good to go. So hi, it's good to see you here. My name is Mike, and this talk today is about approaches to development for small microcontroller class devices. Heavy emphasis on TDD and continuous integration. There's going to be a real old mix in here. There's going to be some tools. There's going to be some build automation. There's going to be some bit of live code even. What excitement. I think we're going to be kind of tight on time, so if it's possible for you to park questions until the end, that would be great. The slide numbers are really prominent on the slides, so just note down one of those and we can go back to them. So just to set the scene a little, I just want to look at some trends in embedded that I think shape the way that we're doing development now. I'm going to caveat this very heavily because I don't have hard data on this. This is based on conversations that I've had with individuals and with teams. But I think this situation of a more library-rich embedded environment is becoming more and more common. Customers, and whether they're industrial or commercial or consumer, they kind of expect more from devices and they want it faster. So it's more and more common for us to be reusing established libs. So I think for every team that breaks new ground using the sort of classic method of, looking at the spec sheet and doing the classic board bring up stuff, there are many, many more teams who are living in this kind of world where they're expected to make a quick start with projects. So the vendors are investing more and more time and money in, this is their responses to make it faster and easier to get started with a working configuration. Some vendors are doing full-blown web IDEs. ARM Embed is one. I think Microchip are doing this as well as an alternative to desktop tooling. So the point and click, you configure the pins, you configure your clock parameters, you push the button, and hey presto, you get a hardware abstraction library that's customized to the functions that you've selected. And it's great in a sense. It gets you started really quickly. That's a useful thing. I find these tools very useful to start projects. But the libraries always have some kind of a testability cost, right? They want you to work in a particular way, and sometimes that can be a barrier to doing meaningful developer testing as the project progresses. They also incidentally generate two of the most dangerous lines that you'll find in any embedded source file, which is this one. And people take that sometimes just a little bit too literally. It doesn't mean put all of your code here. It means there are some initialization hooks that you might require. So a lot of these libraries, they're automated for tooling convenience. They're automated for code. They're optimized for code generation, and not so much for humans to read and maintain, and certainly not for testability. The vendors aren't that focused on the use case where you are testing your code off the target. It's all designed to work well on the target. So we have this challenge of tools being really useful for initial config, but then potentially obstructive as your project moves on. So yeah, a like from Odin and from me as well. So this is a problem. If you've got libraries that are only really usable on the target, then you get drawn towards the target. More and more of your testing can only really happen on the target hardware. So that's a problem with an ever-increasing size of software stack. So why TDD and how does TDD help us? Let me just say up front that TDD is not some silver bullet, right? It's not a panacea. It's not going to immediately make your life easier. It's a difficult thing to practice, difficult thing to grasp, and you are going to have to do some groundwork in your build to make this happen. It's basically a feedback loop that tells you how your code is behaving or the test passing, and it also gives you feedback on the health of your design as your design progresses. It doesn't fix your code for you. That's your job. So there are really two versions of a story for TDD. One is the completely generic one that you see here, and you've probably heard that many times. There are standard arguments for why TDD is a good thing. Then there's the embedded story, the embedded specific story. So I'd say the one that probably stands out from the generic ones is the decoupled code. Right? If you are testing your code off the target, on your host, on your development machine, you are forced to address hardware dependencies. You can't depend on hardware that isn't there, and that's the discipline. But for TDD, for embedded, it starts to get a little bit more interesting. This is the embedded perfect storm, if you like. So the constraints are well known. That's been the sort of defining characteristic of embedded for many, many years. But there are other things that make our lives complex. You might be surprised, I don't know how many people here work in embedded or other technical domains, but despite all these libs, and even with a real-time operating system, it's a remarkably blank canvas compared to other applications. If you look at people doing server development and enterprise systems or GUI development, there are very definite guide rails these people work along. It's not so much the case with embedded. So the kind of industry response to this is, well, more process, we'll do more UML models, we'll do more design. I don't really think that's adequate. I think a diagram is just a hypothesis. The bigger the model, the bigger the hypothesis. It doesn't really reduce risk. Coding standards and static analysis tools, great. I love static analysis tools. I find them very useful. But they don't tell you code's right. They just tell you it's safe and it's doing what it should be doing. It doesn't really tell you that functionally it's correct. So I think TDD and small increments is a rational response to these sorts of challenges. But there are many variants on what a test is. So TDD tests can be run on the host. You run them on your developer machine using your framework of choice. I'll be using Catch and Trompe for these demos. You can run tests on a simulator. You can have tests running on your eval hardware, but still stubbed, using the same stubs and mocks. You've got tests running on eval hardware and actually interacting with the peripherals. And then full-on target deployment, complete system test running the fully integrated hardware. So we're going to be doing some examples with the top one and kind of with the bottom two in this talk. Okay. So a few patterns that I think are worth talking about. I won't be able to get into this in massive depth. I really highly recommend this book if you've not already had a chance to look at it. Jared Mazaros wrote, I guess, what the definitive view of patterns for test and patterns for substitutability, because that's really what testability is about, is the ability to isolate your code for testing by different types of substitution. I'd also recommend Michael Feather's book as well. I think that's a good background for this stuff. But we're going to be looking at mocks, we're going to be looking at stubs, but there's more out there. And a question rather than a statement, but it's worth thinking up front about what are the different concerns within your system. I mean, most of us have some kind of domain logic. Most of us have, obviously, hardware interactions. But what else is there? Because these things are going to help to frame the kind of high-level software architecture of our system. So classic OO. Let's talk about the dependency inversion principle. So this is, I guess, can I say 1990s style OO. The principle is that high-level modules don't depend on low-level modules. Both depend on a shared set of abstractions. And this is a mechanism for teasing apart these dependencies within your code. Abstractions don't depend upon details. Details depend on abstractions. So the best thing about dependency inversion is that it always works. The worst thing about dependency inversion is that it always works, and people overuse it, use it unwisely, use it to excess, and it's very easy to end up polluting your type system with a bunch of very fine-grained, tiny interfaces that makes your code hard to understand. I did smile at Bjarne's reference in the opening keynote. He talked about C++ being hijacked by sort of inappropriate idioms. I think I thought about this when I heard him say that. So I do find it works. I mean, it's usable, but I think it helps when these interfaces kind of coalesce at module boundaries rather than having each and every type in your system. So really simple example here. Here's our abstractions. We've got a couple of types. We've got our washing machine. We've got our indicator LED. So pure virtuals, interfaces. So both sides of what was a direct dependency only know about these abstractions now. Our implementation of the washing machine is expressed in terms of the the abstract indicator LED, not the concrete type. And so that's easily substitutable for testing. Okay, so a typical test with catch and trompe-l'oeil. We create our mock object. We inject that into the washing machine. We run some code and we make an assertion. And the fact of, in case of trompe-l'oeil, we have a requirement up front. We expect that mock object to be interacted with in a particular way. So this is seductively simple, and this is why I think this kind of idiom tends to kind of spread in code bases. It's quite easy to do. The framework supports it very well, but that doesn't mean it's always the right thing to do. A word on mocks before we move on. I find these misused an awful lot. The point about mocks is that it's a way of discovering the requirements, the needs that your code has from other types. It's basically a design process. So when I'm implementing here my, what is that, rinse cycle, my washing machine, incidentally, the washing machine references will become clear a little bit later on. What I'm really doing is I'm discovering the requirements I have from other types. And if you aren't doing that, if you're talking to some third-party library or the hardware abstraction library, mocks don't really do anything for you. You're not designing those things. They're fait accompli. They're there already. Okay. So only mock when it's your design. Don't mock otherwise. So testing direct interactions of a hardware. If you are implementing your own hardware abstraction types like GPIO ports, analog to digital converters, whatever, that's actually refreshingly simple. These kind of state-based unit tests are really fun to write. You do a thing, and then you verify the effects of the thing that you've done. So in this case, I've got a GPIO port. In an STM32 chip, the GPIO has a lower half word and an upper half word in one of the registers for setting or resetting bits. So if you set low, then that goes to the lower half word. If you set high, there's a shift and it gets set into the upper half word. So these are really simple tests to write. As long as you can construct the memory layout of that peripheral register in your test, set the preconditions, and then make verifications about it. It's really simple. So simple construction of the memory that fakes out the memory that would otherwise be in the hardware register, and then placement new at that location. Really simple way to test, and I would strongly recommend that if you can get away with writing these kind of state-based tests, do that in favor of mocks. So you make your types easy to use and easy to place, and then you will write more tests. And when you write more tests, that'll help you improve the usability of your types. So something like GPIO is never going to have a virtual interface in front of it. It's never going to be an abstract interface. The closer you get to the hardware, the less effective virtuals become as a kind of design idiom. So template schemes can be quite effective for, if I have a dependency on GPIO, then I can use a template to use what's effectively a kind of compile time duck typing. But I can use it in combination with mock objects. It's important to note that with mock objects, you're not absolutely compelled to be doing the kind of classic virtuals abstract interface idiom. It works perfectly well for concrete types as well. So in this case, our door status indicator for a washing machine design, this has a couple of methods, on and off. It requires the services of GPIO, which is actually quite a large type, but we only need to mock to substitute the things that we're using. Okay, so we're only using the right function in this case. So our mock object can be very small. We can define that within our test case. Construct our object parameterized with the mock rather than the GPIO type, and we're good to go. Okay, so there we go. So mock GPIO, there's a test case, construct the mock, construct our door status indicator, parameterize based on the mock that we're using this time rather than the real deal GPIO, expect a call to write, and then exercise the indicator. Okay, a couple of quick words about real-time. Who uses a real-time operating system here? Is that fairly common? Some, bare metal only. Yeah. I'm going to nail my colors to the mast here. I really like the RTOS model. I actually find that I can do better design when I'm using a real-time operating system. But there are some challenges. So they tend to be kind of complexity magnets. Tasks in real-time operating systems tend to kind of accrete a lot of responsibilities. And that's sometimes a sign that the design has not been fully worked out. So there are things that we can do to improve this situation. We have the problem of while one, of course, which is kind of a showstopper from a testing point of view. If it never exits, we're going to have trouble doing anything with it. So I've often found as well, when I'm using a real-time operating system, I want to transit from task land into object land, right? I have a more kind of object-oriented design, and I need to find a way of doing that effectively. So with FreeRTOS, for example, we have our task create function, and the one I want you to focus on there is PV parameters, right? There's a single parameter we can pass to this pointer to void. And what do we do with that? Well, we can construct something, an object, pass that in as a parameter. But whatever, there are multiple resources we need to access. We need to access semaphores and queues and mutexes and other typical kind of RTOS constructs. So you can create a struct with a kind of a parameter pack, but that's not ideal either. So what I tend to do is a very lightweight use of templates just to bridge that gap from I have my RTOS create task function that I want to invoke, but I also want to get to route that task run to an object instance that I have. So a couple of very simple templates, a wrapper around create task, a template function which basically replaces what would previously have been our RTOS task. And then when the scheduler runs, it's the function template instantiation of that RTOS task function that gets called. So if I have the same task being created for the same type, let's say I have 3 buttons and I have 3 different tasks for these, well, that's okay. It's the same type, it's the same function, template instantiation, it's the same address. But all it does is casts that one parameter to the object and then passes on to that. It still leaves us with the while one challenge. So a bit of very light touch policy-based design works here. So we can compile time strategize the loop in effect. So we have strategies for forever, which is the default case in our RTOS. And for testability, we can have a specific number of times through the loop. And we end up with our testable blinky, which looks a little like that. So the default template parameter is forever. As I said, that's the normal case. And we can then override for test purposes. So we have a blinky task. We parameterize it to say, I want this to run a single time. We run it, and then we make an assertion about it. So what was previously quite a difficult thing to test, we've adapted to fit the model that we want and to adapt to the way that we want to test. I'll keep this brief. Third-party libraries, stub, just stub. Do the least work that you can do in order to get your code running, to get it to compile, to get it to link, and only do something more sophisticated if there's an absolute requirement to do so. So if there's a return value from a third-party library that's going to affect the way that your code flows, then okay, you may have to do something there. If it's absolutely essential that you know that the right parameters are passed to this third-party API, then okay, you might have to record those parameters in your stub. But the default approach is just stub hard code return values unless it's a significant impact on the way that your code behaves. So test spies are another pretty good approach. These basically just record the parameters that are passed to the function call. but only stub as well when you're impeded. You don't go and create proactively a whole set of stubs for an entire framework unless you absolutely need them in your code. Like most people, you'll probably use a fraction of a library's capabilities. And do please resist the temptation to use mock objects for these. It is almost never the right thing to do. It's just not the right tool. You're not doing design of that library, so you don't really need a mock for it. There's a nice framework called FFF, which I'd recommend you look at if you need a little bit more sophistication in your stubs and spies. Okay, so stub when you need to. A couple of words about testing on the target. There are a lot of reasons to do this. You definitely want to know that your code compiles, obviously. You're going to be compiling every single time you have a commit for the target. Compilers have different quirks, they have different bugs. Standard support is in different places for multiple compilers. Rarely identical. But I've found over time that the TDD tests that I want to run on the host are not really the same tests that I want to run on the target. I write these test on target tests for different reasons. They're really kind of verification tests and integration tests. So I know some people try and get all of their TDD tests running on the target. I found that to be pretty painful. I think you run into size issues and you end up having to kind of chunk your tests into mini suites. I find it difficult, and I also find that it sort of drains the energy from your TDD activity. So over time, I've come to use different frameworks for these. If I'm going to test on target, I use Unity. If I'm doing TDD, I use a modern test-driven C++ framework like Catch. Okay, I use Segar tools for this. One of the challenges is just getting the results back from the target. I use Segar RTT framework, which is it's kind of a telemetry data transfer library that lets you emit data over your JTAG debugger, capture it using a console logger, and get that to a file. So Unity is super simple, really, really low footprint. Will run on, if your code runs on the device, you can probably get some tests running with Unity on the device. So the mechanics of this are that I have to implement some putchar that works over that mechanism, or RTT. I have to let Unity know that I want you to use that. That's how we're going to putchar. And then when I'm capturing the log, I have to use a Segar tool to do that. Now you could do this with ARM semi-hosting, you could do it with a UART interface. It's entirely up to you how you do this, but I tend to have the Segar tools within my build anyway, including the RTT framework, so that works pretty well for me. And whatever you do, you're going to have to make significant changes to your build if you don't have any tests in there at the moment. It takes a little bit more internal modularity to get this working effectively. You're going to have to substitute implementation of link time in order to get that sort of substitution of stubs and spies. So you will find that you have to look at how your build is chunked. And also use that as a way of, I guess, constraining dependencies within your build. It's good to kind of reinforce your software architecture using the build if you can. And talking about build, CI. So TDD is about designing testable code. It's about designing good code, getting it right. But what happens with those little increments? How do you actually get to the next step? So the way I think about CI build is kind of as a bridge. It takes me from working on the host to testing on the target. I very, very rarely build manually now for the target platform. It's virtually always automated. It's virtually always through the CI build. Never, just rarely. Sometimes you're going to have mysteries to solve and you still have to do it. So all of this is possible with open source tools. We're going to be using Jenkins here as an example, but we'll look soon at all the different elements that are involved in the build. But I'll give you a walkthrough first of all. So I build on every change. Yep, so I use git commit hooks to do that. The way that Jenkins works, it will index the entire repository, so any commit on any branch will result in a build. So you build and run the unit tests on the host, right? You're running on a AMD 64 architecture. usually a Linux box for me. And any failure, you stop the line. And by stop the line, I mean two things. One is you stop the build pipeline, and the other thing is you stop the production line. You stop coding. You don't keep adding on top of that failed test. So you diagnose and fix the problem and you move on. Recompile for coverage. I use Clang and LLVM and LLVM Cov. I find it's a really nice tool. I archive the coverage reports on the server as well in case I want to go back and look at them. Recompile tests and rerun using the sanitizers. So address sanitizer memory and undefined behavior as a minimum. Thread sanitizer wouldn't make sense. It's an ARM Cortex-M device, so that's not really going to be applicable. That's a slow part of the build, as we'll see. Static analysis, Clang tidy, Clang static analyzer. We're kind of getting into slightly more subjective territory here. You've got this kind of difficult call about what you do with Clang tidy issues. It can be a bit noisy sometimes, so sometimes you have to dial back the severity of that, or say, I'm going to treat that as an advisory and I'm going to let the build move on. Other people take a stricter view and say, well, if you're not taking it seriously, why is it in the build? Fail the build. So yeah, it's a judgment call on your part. Build and deploy the test on target tests always. So using Unity and using the Sega RTT framework as we looked at. This is a little bit convoluted, so you have to deploy and run the tests. You have to have the logger running, and then you have to deal with timeout as well, because if your code ends up in a hard fault handler, then you're going to be waiting a long time, the longest cup of coffee ever. So you need to kill the logger process and say, didn't work in the event of some timeout. So you're scanning the log for a success indicator, and Unity is pretty clear with that. Start of line, okay. In the absence of that, all bets are off. Stop the build again. Building the real deal binary, in multiple, you're building the ELF and the X files in multiple configurations. So debug, release min size, and release with debug info. Archive the whole lot, and then finally deploy that to the target. Okay, now really there's a lot of value in there, but the start and the end of that, to me, are the most kind of liberating parts. Is the fact that I know that every single commit is going to get built, and every successful build is going to end up in the target. I've wasted too many days, weeks, months thinking you're chasing phantoms on the target hardware, doing debugging hardware sessions, and just not being really clear what's on there. Did I make that change before I flashed that, or do I have to do it again? Or what version is this? What branch am I on? It's really clear with CI because the last time this was all green, that's what's on the board. That's what's on your eval hardware. The one thing I would add to that is fuzzers don't have that at present. So this is what's involved. We use, I don't know how many of you are using Docker as a kind of CI containerization mechanism. Really useful tool. So Docker plus Jenkins and a Jenkins file, CMake build as well, and obviously Git for commit hooks and your source, not least. So there's a kind of symbiotic relationship between these things. The Jenkins is going to run assuming that there are certain tools and tool chains on the host environment. That's Docker's job to provision those. The Jenkins file is mostly going to be running targets that are in your CMake build, so they have to be kind of co-versioned. So you have to move these on. There's a little bit of elasticity there, but you can end up in incompatibility issues. So if you're changing the structure of your build, you're probably going to have to change your Jenkins build as well. Okay, a couple of very smart guys once wrote this statement. And so this is the stuff that we've been talking about, the TDD and the continuous integration. This is, for me, it's a way of getting to that idea of correct. Right? I know what correct is because my tests are passing, the sanitizers aren't firing, stack analysis is all green, Clang tidy is all green, etc., etc. It's running on the board. And then it gives me a test harness and a safety net for getting to the next step. Whether the next step is fast, the next step is small, it's all good. Okay. hardware. Let me introduce you to our hardware du jour. It's the washing machine. I know you can't all see that. It's kind of awkward, so I've got it up on the screen here as well. This is a design that I've created to help people to practice these things, to help practice test-driven development and CI. Understandably, if you're working on, let's say, safety-critical systems, you're going to feel a little bit nervous about just randomly experimenting with new design approaches and new test approaches. So it's good to have a safe sandbox to do that in, and that's what this is for. So it's a platform for deliberate practice. It's basically a code kata, but it's a code kata backed up with hardware as well. So there's a functional spec, there's a hardware design, and the idea is to use that as a vehicle to explore TDD, continuous integration, and other techniques. Okay, so let me tell you about the design of it. I had to think about some of the challenges in embedded, what makes embedded difficult. So there's different programming models in there. You have to work with timers, you have to work with interrupts, there's polling as well. There's DMA if you want to use that for the analog to digital conversion. There are finite state machines within finite state machines within finite state machines on this. It's actually a reasonably tricky control problem. And lots of different stimuli, lots of events. There's a mix of sensors, there's analog sensors, there's button presses, there's user actions, there's timers, etc. Okay, so we're going to put this to work. Now, bear with me just a second. We're a little bit late getting set up, so I just need to verify a couple of things that I actually have a connection to. Yep. I have one here. You can't see it. It's on the seat. So just for clarity, USB connection. I have a Sega there, honest. I have the hardware there. I have a webcam, which is very badly set up and badly focused, but when it comes to actually getting this running, we'll see if we can make it work. So I am going to start my CI build, and I am going to try and unmirror the screen. Mirror. Let's see if this works. Okay, did that work? I think it did. Okay, so let me just flip back the slides for a moment just to kind of explain the... So this is the kind of top level state machine design for the washing machine, an actual state machine design, like I'm some kind of professional or something. So the top level is, you go kind of from a selecting state into an operating state. So you're pressing buttons to select the program. You close the door, it's a very significant event. You close the door and then you're ready to run the program. So what we're going to be doing is precisely that. We're just going to do some TDD of going from that kind of open to ready state. And just to make it interesting, to make this a non-generic TDD example, we're going to do that using a real-time operating system task and see how we can TDD that. Okay. Oh, and yeah, I've done these before. It gets kind of really confusing when people have conversations as well. So if you don't mind park questions then, I'll be very happy to take them. But let's make a start. So our problem is a task, right? Our RTOS task. And I'm going to just jot down some tests here, kind of a to-do list. So what we do is when we read a high signal on the slide switch, that means the door is opened. When we read a low signal, that means the door is closed, right? So we're going to go through our washing machine. Our washing machine already has a logic in there to switch on the LED, so we're not going to be worrying about that. So it's just the task implementation. So when high signal is read, let me go into presentation mode for this. It'll be easier. Can you see that okay? Is that legible? Cool. So when we read a high signal, sets door status to opened. Nobody wants to see me typing, so I'm going to copy and paste some of this. When a low signal is read, states door status to closed. And then we've got the looping logic as well, so I'm going to say when run multiple times, or run a loop, sets door status multiple times. Oops. So in defense of my finger fluffs, I was using Emacs until about 2 months ago. I'm really not used to IDEs trying to help me, so you'll have to put up with those. Okay, so implicit in that last one is that there's some commonality in the first one, so I'm just going to capture that. Say when run once, this. Okay. So Ken Beck recommends writing a test list for what you're about to do. It's like a mini roadmap, a sort of a do list. I find increasingly we're using Catch that I'm just writing the code. I don't implement all the tests, just one at a time, but all the same, it's useful to do. So what we're going to need here, well, we're going to use a mock object, or washer, that we're going to use to set the state of the LED into. We need some memory. Memory out. Call it fake memory. And the only register in here that we're interested in is the input data. The rest of it is not going to be used in this scenario. So I just made that explicit and initialize it there. And finally, we want to construct our GPIO using placement new. So GPIO port equals standby 2 port. Place that. Okay, so these are the two dependencies our task needs. The task needs GPIO. It's going to read from that in order to find out the state of the door switch. It needs to know the model to talk to. That's our washing machine. So the final missing link here is we need our task, door handling task. And our hypothesis here is we're going to inject the washer and the GPIO, and that's all just going to work splendidly. So this is our system under test, right? That's the thing that we're testing. Everything else is kind of a collaborator. Okay, excess elements struct initializer. So compiler speak for please implement a constructor. So let's do that. So what do I need here? I need the washing machine, and I need the GPIO port. What happens when I run the tests? Okay, so I'm back to a passing state, not actually doing anything with them yet, but we're compiling. So I can go and do something a bit more real now. So I'm going to set my expectation that the washing machine gets called. Require call, mock washer, door opened. Okay, that's in the high state. What do I have to do to make that happen? Well, I have to make that pin go high for the door switch. Fake memory, input data. That's door switch pin. There we go. Finally, I'm going to run the task. So door handling task, door run. It doesn't exist. Classic TDD, right? You're coding against API that doesn't even exist yet. So I have to create that. Oops, not like that, I don't. C-line trying to help me again. Create new function, there we go. So what's the bare minimum I have to do to make this test pass? What's the smallest thing that can possibly work here? Well, I'm going to need the...
Always call.
Sorry?
You always call.
Just call the washing machine, right? Just absolutely. Make a call, yeah. So there's my washing machine. I'm going to need it at the field, obviously. Oops. Let me just change the name of that. I have to initialize it here. Washing in. There we go. typo. And then invoke it here. Washing machine, door opened. Right, that's the simplest, crudest thing I can do to make the, oh, not quite. Assertions 5.1 failed. What's going on? Oh, absolutely. Yes. Sorry, where am I doing that? Ah, yes. Good catch. There we go. There we go. So, that's one case. What's the next one? So, another require. We require call, mop washer, door closed this time. Don't need to do anything to set the memory for this because it's already set low in the test setup. So I just need to run the task, run. And 2 failures. So it fails twice because it's been called in a way it didn't expect, and it's not been called in a way it did expect. So we get 2 assertions with the price of 1 there, like some strange supermarket offer. So back to my task. What we're doing here. So the kind of obvious next step is I need to obviously get the field for the GPIO port reference, GPIO port. I need to initialize that. GPIO. And then I need to conditionally call only if the pin is set. So if the door switch pin is high, set, then we call opened. I'll just run that again, see what happens. Okay, so we're down from 2 failed assertions to 1. So we just need to put the alternate case in now. Door closed. Okay, passed. Cool. So, let me just flip back to the test. Finally, we have the loop logic, right? So I'm going to be lazy here and just do a little copy again. So I'm going to say that when we're called multiple times, and I'm leaving I'm assuming that's just door closed again. It's kind of the simplest case. So that's not going to work now. There's no looping logic in there. And also we're not instructing our task to loop a number of times. So I'm now going to have to fix that. So what I do is I'm going to make this explicit and say, well, your policy is you're going to do this once. Your policy here is you're going to do this twice. Okay, and I have to make the change to task itself. So that should compile, still failing, right? Still expected to be called twice when it's only been called once. So my next step is just to do something with that policy. Okay. Cool. Not finished though. I want to throttle this task a little bit. Even if it's a low priority task, I don't want it running that often. So I'm going to put an explicit delay in here and say you're going to delay for 50 system ticks. Okay. Linker error. So I'm using some RTOS API, but that's not linked. So in order to make this compile, I just have to define a stub for that. Now I could make some assertion about that, but what's the point? It's 50. I'm going to assert that 50 is 50. It's just it's a literal value. So it doesn't really serve any purpose for me to then do anything sophisticated with my use of that RTOS API there. I just need it to work. I just need it to compile, because it doesn't affect the flow of my code at all. If I was working on some safety critical system and it was absolutely vital the right value was passed, double entry bookkeeping sort of approach, then maybe I'd have to do something to record the values that were passed in as arguments. But for now, it works. Okay, so just going to go back to my test. Say, I think that looks all right. So I've got a final little bit of bookkeeping to do here, and that's in my builder. I just have to wire this up so that the task is actually initialized when my system starts. So what do I need? Yeah, not that's for sure. Static platform, door handling task, and I'm going to inject the washer. So that's the real deal washer in this case, and the real deal GPIO. And so in case you're wondering why it's static, the way the RTOS scheduler works, at the point where the scheduler starts, it resets the main stack pointer. So if you have anything that's of automatic storage duration, it's gone. Well, it's not gone, but it's not safe to use. It's going to be used pretty quickly. And so I need to, what else do I need to do? Create the task, give it the address of my new task object, door handling task, give it some very imaginative name, and guess at stack sizes. I'm plucking numbers from the sky here, time-honored tradition. Okay, use of task, yeah, template without saying that's actually a template. There we go. Too few, oh, right, did I? Yeah, okay, I meant to do this, that's why. Okay, so it runs forever unless I say otherwise. Okay, so I'm going to get logged into my CI server. Bear with me a second. A little rushed in the prep, so a couple of steps I was hoping to have done. There we go. I'm going to open my pipeline here and see what happens. Okay. Right, I'm going to commit. I like to share my state of mind and commit messages. Okay. So I'm going to flip back to the build here. So you can see, because I've got a git commit hook, that started immediately. I'm going to see if I can do something clever with VLC. Okay. Okay, there should be a small flash on that board as the target test build gets deployed and it starts doing logging on it. I hope you could see it. There we go. The light's kind of dim when the sanitized builds run. It's pretty intense. I can get quite a fast build. I've got a Xeon workstation at home, and it's pretty zippy. Not so good on a laptop, but we'll make do. Okay. So, very little flash there. It's now reading the logs, checking that we're good to go.
Wait, were these the exact same test?
Sorry?
Were these the exact same test?
So the test that's running on there was that there was a kind of a noddy example I did, which is just reading from GPIO. It actually reads from the start button. So it was like one sample test. So it's just reading from the GPIO, but with the assumption that it's configured in a particular way. So the buttons there have a pull-up resistor on them. So you can say with confidence that it's going to be high unless somebody's standing there with their finger on the button, which we might try in a second. And there's our test completed. So end to end in, what was that, 1 minute, 28 seconds. That's not bad. So the moment of truth, that's my LED. I'm expecting it to go on. That's the switch. Please let this work. Ah, failure. What have I done? Spectacular. Debugging, yeah. I don't think we're going to have time for debugging, but that would most certainly be my next step. Sorry?
The delay is nothing to do.
Oh, true, but yeah. No, it should still work with the switch on and off. That's strange. Let me just look at the builder. Great task, GPIC, yeah. Okay, looks feasible. So I'm going to invoke the standard mantra of the embedded systems developer here and say, it must be a hardware problem. I'm just gonna flip to system view and we'll have a look at this on here, see if we can see what's happening. It might shed some light on this. Okay, that task is definitely not registered. Okay, which leads me neatly on to my next point, which is that just because you're doing TDD doesn't mean that debug on hardware goes away. You're still going to have to do that. Unfortunately, I think we're going to be out of time to really diagnose this, but hey, there you go. There are, I'd make a point about the deploy and test on target, which is that these kind of tools, these kind of diagnostic tools are immensely useful as well. So you got to look at the kind of overall economics of your build and debug and test scenarios. You can invest an awful lot of time in writing tests that run on the target when you might be able to get a quick visual eyeball of this by just pressing a couple of buttons, capturing some telemetry. And if you've got a system that can be tested in 30 seconds or 60 seconds, then that's a pretty low investment to get some insight into the way that your code's behaving. Sorry for our failed demo there. I'll have a look at that in a bit more detail. There's maybe something lurking somewhere else in the build. So I just want to flip back the slides and we'll wrap up with a couple of sort of closing comments here. Okay. So the points I would make is that small increments make for very small mistakes. They make for sort of containable mistakes, like that one there, for example. I'm only a few moves further than the last commit. Be careful about targeting your test and target. It can be a massive investment of time and effort. So pick the right tests, pick the ones that give you the most value. And like I did with the RTOS create task there, adapt to fit your model, but don't try and boil the ocean. Don't try and build an OO framework for something that's just intrinsically never going to be OO. I see a few attempts at that, and it doesn't really look like a good policy. And if it's not impeding you, stop worrying about it. Don't even stub it. Unless it's failing to link, just put it out your head. And I would say that the how is going to be probably your biggest barrier. The thing that you use most frequently is a hardware abstraction library. So you might want to think about selectively refactoring to something better. Because although you can get started very quickly with vendor hows, it can become a real burden over time. So refactor the things that are causing you the most pain. And the CI build, bring that right to the doorstep of your device. Be hands off with this stuff. You can trust yourself to build the pipeline, but don't trust yourself to second guess it. You'll let it make a call on whether that code is good enough to put on the board. And optimize for develop and test on the host. This is where you spend most of your time, is writing code, running tests, writing tests. So make that fast. And sometimes that means that the vendors really want to do this at the moment and bring IDEs and platforms closer and closer together. There's actually a case for teasing them a little bit apart. And where you have embedded tools that can let you test on the platform and diagnose on the platform, do that. Yep. So play to the strengths of the different tool chains. There are different use cases. Great books. Really recommend James Groening's book. Fantastic read, whether you're working in C or C++. One of the best books ever written about test-driven development, in my opinion. Jeff Langer's book is an excellent introduction to TDD for C++. And Michael Feather's seminal book on working effectively with legacy code is a fantastic read. Should be on everyone's bookshelf. That's it. Thank you very much. Questions?
Hi.
Hi.
First of all, thank you very much. I think it's the one talk this week that I don't feel like an imposter in the C++ conference. It looks like what I do every day. So,
right.
Quick question. So, clearly having that whole setup for your CI integration is fantastic. How hard it is to set up all of those? Mainly, so you need to have a machine, hardware dedicated hooked on the server that gets flashed with the test and then gets flashed with the
So the best way to do this is I run this locally all the time. Right? I use a Docker container, and I just have the Docker container running on the workstation that I'm working on. So the nice thing about Docker is portability. So the same build that you have running in the cloud, pretty much. The cloud, unfortunately, doesn't have a USB port, so you can't plug in your JTAG debugger. But the ability to do that extra step running locally in a workstation, I think is fantastic. It is an investment. It's probably not as big as you think. If you looked at the kind of first phase of that build, virtually everything I'm doing is recompiling and rerunning the same tests. So I compile and run the tests in different configurations. I compile and run them with the sanitizers. So you get a lot of value back with just a little tweak to tool chains. But start small, right? Just start with build, test, green light, and then start to kind of embellish on top of that.
Right, so the actual TDD loop inside of the development machine, that's fantastic, and we do that all the time.
Yeah.
Feels like that extra step, we actually started doing this, right? We started building for running the test on the platform, on the target, and that was a nightmare. And it was way too long, right? Because your feedback needs to be quick. You need to write, get that green, write a new test, refactor, whatever. So that needs to be quick. And if you have to, flash the target every time, it doesn't scale at all.
It does. It drains the energy out of TDD. It's not a good way to do it.
Exactly. It's no longer TDD.
It's a verification step, right? And that's why I say that it's better to think about what the tests are that you want to run in the hardware, make it a subset, make it targeted, and make it the things that are going to give you the biggest value from running on the hardware rather than on the host.
Last question, and I think it's still related. Works fine to have all those steps. It took a minute and a half, but it's a tiny program.
Right.
Doesn't scale, it seemed to me, when compiling takes, just one compilation takes 2 minutes. For example.
Yeah, I mean, the bigger the system, the more you might want to push the majority of your build in the cloud. The only things you really need is some agent running locally that at the right point in your pipeline is going to say, oh, I have some work to do now, and I'm going to deploy to the target eval board. So that's something you can do as a divide and conquer thing. So you can have the majority of your build running on really high performance kit to get speed with the sanitizers, and then some local build agents that are just going to do the things that they need to do with sort of physical hardware. That takes a bit of orchestration, usually networking and security issues, everything else, the usual gamut of problems. But if you really do find your builds are slow, then you can sort of divide and conquer that way.
All right. Thank you so much. I guess I would like to continue to talk. This is fascinating.
Yeah, absolutely. Come and have a chat.
All right, thanks.
Any other questions? Yeah.
Yeah, I had a comment on the code in the live coding session.
Yeah.
You were passing in references and then saving them as private members, and the references were actually referencing things that were of global storage duration.
Yeah.
You could have been using non-type template parameters and saved some space in the object.
Right. Sure.
Yeah.
Yeah.
And I'd also like to comment that there aren't very many embedded talks where I don't want to heckle, but this was a good one.
Okay. Good to know. Thanks for that. I'll take that as an endorsement. Any other questions? Okay. Cool. Come and give me a shout if you want to. Thank you.